There is a star in our galaxy that is older than the universe. Read that again. Let it sink in. The universe is 13.8 billion years old. We know this with remarkable precision, measured from the echo of the Big Bang itself, confirmed by multiple independent methods, refined over decades of observation. It is one of the most well-established numbers in all of science. And yet, 190 light-years from Earth, there is a star that appears to be 14.5 billion years old. A star that predates the cosmos that contains it. A star that, by every law of physics we understand, cannot exist. Its name is HD 15283, but astronomers have given it another name. They call it the Methuselah Star, after the biblical patriarch said to have lived 969 years, the oldest human in Scripture. This star has lived longer than Scripture, longer than Earth, longer, apparently, than existence itself. Tonight, we explore the impossible stars, objects that break our models, defy our theories, and force us to question whether we truly understand how the cosmos works. Because sometimes, the universe doesn't play by the rules we've written for it. To understand why a star older than the universe is a problem, we first need to understand how we know the age of the universe at all. The answer comes from the oldest light in existence, the cosmic microwave background. This is the afterglow of the Big Bang, radiation released 380,000 years after the universe began, when the cosmos cooled enough for light to travel freely for the first time. That light has been traveling ever since, and we can still detect it today. It fills the entire sky, faintly glowing at a temperature just 2.7 degrees above absolute zero. By studying its properties, its temperature, its tiny fluctuations, how it has been stretched by the expansion of space, scientists have calculated the age of the universe with extraordinary precision, 13.787 billion years, plus or minus about 20 million years. That's our number. That's how old everything is. Now, how do we determine the age of a star? This is more complicated. Unlike the cosmic microwave background, which gives us a single, unified measurement, each star must be dated individually. We look at its brightness, its temperature, its chemical composition, its position in its life cycle. We feed these measurements into models of stellar evolution, mathematical simulations of how stars change over billions of years. And here's where things get interesting. Because when astronomers first tried to date HD 140283, the numbers came back wrong, not a little wrong, catastrophically wrong. HD 140283 has been known to astronomers for over a century. It was first catalogued in 1912 by W.S. Adams at the Mount Wilson Observatory, noted for its unusually rapid motion across the sky. The star moves fast, 800,000 miles per hour. It crosses the width of the full moon every 1,500 years. This velocity is a clue to its origin. HD 10283 is not a resident of our galaxy's disk where the sun lives. It's a visitor from the halo, the ancient spherical cloud of old stars that surrounds the Milky Way like a ghostly shell. Halo stars are among the oldest in our galaxy. They formed early, before the Milky Way had fully assembled, before the disk had flattened out. Many of them were born in smaller dwarf galaxies that were later cannibalized by our own. Scientists believe HD 14283 was likely born in one of these ancient dwarf galaxies, which the young Milky Way swallowed more than 12 billion years ago. The star retains its elongated orbit from that cosmic act of cannibalism, looping in and out of the galactic plane like a messenger from the deep past. But it was in 1951 that HD 140283 became truly strange. That year, astronomers Joseph Chamberlain and Lawrence Aller analyzed the star's spectrum and discovered something remarkable. It was composed almost entirely of hydrogen and helium, the heavier elements that make up most stars. Iron, carbon, oxygen were almost completely absent. Its iron content was 250 times lower than the Sun's. This was a revelation. In astronomy, elements heavier than helium are called metals. and they can only be created inside stars. The first generation of stars in the universe was made purely of hydrogen and helium, the ingredients left over from the Big Bang. When those stars died, they scattered heavier elements into space. Each subsequent generation of stars incorporated those metals, building up the chemical complexity of the cosmos. A star with almost no metals must be ancient, formed before the universe had been enriched by stellar deaths. HD 1400283 was one of the oldest stars ever found. But how old exactly? In the early 2000s, astronomers attempted a precise measurement. They calculated HD 1400283's distance, luminosity, temperature, and composition. They fed everything into their best models. The answer came back, 16 billion years old, 2 billion years older than the universe itself. This was a serious problem. If the age was correct, then either our understanding of stellar evolution was fundamentally flawed, or our measurement of the universe's age was wrong. Both options would require rewriting textbooks. In 2013, astronomer Howard Bond at Penn State led a team to solve the mystery. Using the Hubble Space Telescope's fine guidance sensors, some of the most precise measuring instruments ever built, they determined the star's distance with unprecedented accuracy. Distance matters because it affects how bright we calculate the star to be, and brightness affects how old we calculate the star to be. Get the distance wrong, and you get the age wrong. They also refined their understanding of the star's internal structure. HD 1400283 has an unusually high ratio of oxygen to iron, which changes how it burns its fuel. They factored in the diffusion of helium from the star's surface back into its core, which affects its appearance. After all these corrections, the new age came back, 14,146 billion years, plus or minus 800 million years. Better, but still impossible. 1446 billion years is still older than 13.8 billion years. The star still predates the universe. But here's the key, that plus or minus 800 million years is crucial. When you account for the uncertainty, the lower end of the age range, 13.7 billion years, is compatible with the universe's age, just barely. Subsequent studies have continued to refine the estimate. A 2014 analysis brought the age down to 14.27 billion years. A 2021 study using astroseismology, measuring the star's internal vibrations, suggested 14.2 billion years. Another 2021 paper, using updated stellar evolution models, proposed the star might be closer to 12 billion years old. The estimates are converging. The Methuselah Star is almost certainly not older than the universe, but it's close, uncomfortably close. It formed in the first few 100 million years after the Big Bang, making it one of the oldest objects we have ever directly observed. It is a survivor from the cosmic dawn, a relic of an era when the universe was young and dark and largely empty. But the Methuselah Star is not the only impossible object in the sky. In 2011, a team of European astronomers led by Elisabetta Caffau announced a discovery that, in their own words, should have been impossible. They had found a star in the constellation Leo with the cumbersome name SDSS J102915 Pile 72927. Like HD 1400283, it was ancient, over 13 billion years old. But unlike the Methuselah Star, this one wasn't just metal poor, it was almost metal-free. Its metal content was 20,000 times lower than the Sun's, the lowest ever measured in any star. It was composed almost entirely of hydrogen and helium, with only the faintest trace of heavier elements. It was, in chemical terms, almost indistinguishable from the primordial gas that filled the universe just after the Big Bang. And that's the problem. According to the widely accepted theory of star formation, a star like SDSS J102915+172927 cannot form. Stars are born when clouds of gas collapse under their own gravity. But as the gas falls inward, it heats up, and hot gas resists compression. For a star to form, the gas needs to cool down. to shed that heat somehow. In modern star formation, metals do this job. Carbon and oxygen are particularly effective at radiating heat away, allowing gas clouds to cool and collapse into stars. But in gas, with almost no metals, cooling is incredibly inefficient. The gas stays hot. It can't collapse into small clumps. According to the theory, metal-free or near metal-free gas should only form massive stars, giants that burn hot and die fast. SDSS J295 plus 172927 is not massive. It's smaller than our Sun. By the rules of star formation, it should never have been able to form at all. A widely accepted theory predicts that stars like this, with low mass and extremely low quantities of metals, shouldn't exist, Caffo said. The clouds of material from which they formed could never have condensed. And there was another mystery. The Big Bang created not just hydrogen and helium, but also a small amount of lithium. Primordial lithium should still be present in ancient stars. But SDSS J102915 plus 112927 has 50 times less lithium than expected. Where did it go? How was it destroyed? No one knows. This star exists in a forbidden zone of stellar physics, a region of parameter space where theory says nothing should be able to survive. And yet there it is, burning quietly in the halo of our galaxy, 13 billion years old, a living contradiction. If some stars shouldn't exist because of their age or composition, others shouldn't exist because they refuse to die. In September 2014, astronomers detected a supernova, the explosive death of a massive star, in a distant galaxy. They designated it IPTF-14HLs and expected it to follow the standard pattern, rise to peak brightness over a few weeks, then fade over about 100 days as the explosion cooled and dimmed. Instead, IPTF-14HLs did something unprecedented. It stayed bright for 600 days, and instead of fading smoothly, it fluctuated, brightening and dimming at least 5 times over 2 years, as if the star was exploding over and over again. Then, astronomers looked through archival data, and they found something that stopped them cold. At the exact same position in the sky, there had been another explosion, in 1954, 60 years earlier. The same star had apparently exploded, survived, and exploded again. This supernova breaks everything we thought we knew about how they work, said lead researcher Iea Arkavi. It's the biggest puzzle I've encountered in almost a decade of studying stellar explosions. Supernovae are supposed to be terminal events. When a massive star runs out of fuel, its core collapses catastrophically. Either a neutron star or a black hole forms in the center, while the outer layers are blasted into space. The star is destroyed. There is no coming back. But IPTF-14HLs came back, multiple times. Astronomers have dubbed it the Zombie Supernova. The star that exploded was at least 50 times more massive than our Sun, possibly much larger. One hypothesis is that it was undergoing what's called a pulsational pair instability supernova, a theoretical phenomenon that had never been observed. In this scenario, the star's core becomes so hot that energy converts directly into matter and antimatter. The resulting instability triggers a massive explosion that blows off the outer layers, but leaves the core intact. The star stabilizes, builds up more material, and explodes again, and again, until finally, after multiple eruptions, the core collapses into a black hole. But even this theory has problems. The energy released by IPTF-14HLs was greater than the models predict, and the star still had hydrogen in its 2014 explosion, hydrogen that should have been expelled decades earlier. These explosions were only expected to be seen in the early universe and should be extinct today, said co-author Andy Howell. This is like finding a dinosaur still alive today. If you found one, you would question whether it truly was a dinosaur. IPTF-14HLs finally faded after more than 1,000 days, 10 times longer than any normal supernova. What remains is still a mystery. But for 3 years, the universe showed us something it wasn't supposed to. A star that died and died and died again and kept coming back. There is a limit to how massive a star can be. It's called the Eddington limit, named after the physicist Arthur Eddington. And it works like this. A star is a balance between two forces. Gravity pulls inward, trying to collapse the star. Radiation pressure pushes outward, generated by the nuclear fusion in the core. In a stable star, these forces are in equilibrium. But as a star gets more massive, it burns hotter. The radiation pressure increases. At some point, the outward pressure becomes so intense that it overwhelms gravity and starts blowing off the star's outer layers. The star can't hold itself together anymore. For decades, the accepted limit was around 150 solar masses. Stars larger than this should tear themselves apart almost immediately. They should be physically impossible. Then, in 2010, astronomers found R136a1. Located in the Tarantula Nebula, a star-forming region in a satellite galaxy of the Milky Way, R136a1 was initially measured at 265 to 320 solar masses, more than twice the theoretical limit. It shines with a luminosity of several million suns. It is, by a significant margin, the most massive star ever discovered. How can it exist? The answer appears to be that the Eddington limit is more of a guideline than a rule. Each star has its own limit, depending on its composition. Stars with fewer metals can have higher limits. The early universe, which had almost no metals, may have produced stars of 300, 500, even 1,000 solar masses, behemoths that burned briefly and died spectacularly. R136a1 formed in an environment with relatively low metals, allowing it to grow to impossible size. It's also losing mass rapidly, shedding material at a rate that will eventually bring it below the limit. But for now, it exists in a state that our textbooks said was forbidden. Recent measurements have revised R136a1's mass downward, perhaps to 200 solar masses, still enormous, but somewhat less extreme. The star continues to be studied, its properties refined. But even at the lower estimate, it remains a challenge to our understanding of stellar physics. The universe, it seems, is not constrained by our calculations. What do these impossible stars have in common? The Methuselah Star, older than time. The forbidden star in Leo, formed where nothing should form. The Zombie Supernova that refused to die. The stellar giant that exceeded the mass limit. Each of them represents the same fundamental truth. Our models are incomplete. This is not a failure of science. It's the whole point of science. Every impossible object is a gift, a data point that doesn't fit, a measurement that challenges assumptions, a phenomenon that forces us to think deeper. When the Methuselah Star appeared to be older than the universe, it didn't break cosmology. It refined our understanding of stellar evolution, improved our distance measurements, revealed the subtle ways that composition affects aging. When SDSS JPON0291572927 formed in the Forbidden Zone, it didn't invalidate star formation theory. It showed us that the early universe may have had cooling mechanisms we don't fully understand. Perhaps dust grains, perhaps turbulence, perhaps something we haven't imagined yet. When IPTF 40-inch exploded again and again, it didn't overturn our understanding of supernova. It revealed a rare, extreme phenomenon that pushes stellar physics to its limits, and perhaps points to new physics we haven't yet discovered. The impossible stars are not anomalies to be dismissed. They are teachers. They are guides. They are the universe saying, look closer, think harder. You haven't figured it out yet. There are roughly 200 billion stars in the Milky Way alone. And for each one we study, there are billions more we have never examined. Somewhere out there, right now, there are stars that would shatter our remaining assumptions. Objects so strange, so unexpected, that they would force us to rewrite everything we think we know. HD 140283, the Methuselah Star, is just 190 light-years away. close enough to see with binoculars. It has been burning since before the Earth existed, before the sun ignited, before most of the stars in the sky were born. It watched galaxies form. It watched the Milky Way devour its home. It has been falling through the dark for 13 billion years, carrying the chemical signature of a universe that had barely learned to create anything heavier than helium. And it will keep burning for billions of years more, long after our sun has died, long after humanity has vanished or scattered to the stars, long after the Earth itself has been swallowed by a red giant sun. It should not exist, but it does. And in that simple fact lies the deepest lesson the cosmos has to offer. The universe is stranger than we can imagine, more ancient, more resilient, more full of wonder. We are only beginning to read its secrets.